Hello everyone and welcome to Keeping Tabs on Chemistry. In this video we are going to talk about percent yield. So the reality of chemistry is that nothing reacts ideally in labs. So scientists use something called percent yield to investigate how well a reaction has occurred. So percent yield compares the actual yield of a reaction to the theoretical yield as a percentage. So we're looking at how much we got versus how much we should have gotten in this experiment. So here's the equation that we're going to use. Actual yield divided by theoretical yield times 100%. This is a part over the whole percentage. So if you have a pizza and you have 8 slices out of the 10 original slices you have 8 over 10 times 100%, you have 80% of the pizza. It's the same idea with percent yield. If I get 8 grams when I should have had 10 grams, that's 80% yield. Now, this is very easy to confuse with percent error. We learned percent error in the beginning of the year. Percent error is looking at what percent you got wrong, not how much you have. So that's theoretical minus actual over theoretical in absolute values times 100%. So make sure that you're getting these two equations right. You don't want to get them confused. Right? One is how much you have, one is how much you got wrong. So, actual and theoretical yield are both amounts of product. We've been dealing with stoichiometry where we're starting with an amount of reactant. Here with yields, we're talking about how much we have produced, how much we have yielded. These are all synonyms for that arrow in our chemical equation. So the actual yield is the amount that you got in lab, how much you actually have in your hands or in the beaker um, from the experiment. So theoretical yield is something that you have calculated using stoichiometry. It's completely theoretical. It is not a physical reality. You've sat there, you've done math. This is what we've been doing for most of Unit 6. We've been working on calculating theoretical yields. So the steps to determining percent yield. You first need to balance the chemical equation, right? This is a theme we've been seeing all throughout Unit 6. Then you need to determine what information is given to you. Another theme we've been seeing in this unit. You're going to determine the actual yield. Now, the key thing here is I'm saying determine. Right? The fact that I've used the word determine means this is not a calculation. You are going to look at the information given to you and you are going to pick which one is your actual yield. You need to calculate the theoretical yield. This is not a determine. For calculating theoretical yield, that is stoichiometry. And then you calculate the percent yield. Again, another equation. You're going to do your actual over your theoretical times 100%. So the tricky part here is step 4. You need to be careful because sometimes step 4 is what we call simple stoichiometry. I give you one product, or I'm sorry, I give you one reactant, you calculate how much product, but it could be a limiting reactant problem. Remember, the way we distinguish a limiting reactant problem is if you're given 2 or more reactants, and you have to decide, well, which one is going to be used up first. So if it's a limiting reactant problem, you need to do 2 lines of stoichiometry and pick whichever one is less. Okay, so there's an example that's already worked out in your notes, so I'm going to walk you guys through it now. If excess amounts of carbon monoxide react with 8.60 grams of H2 to produce 35.7 grams of CH3OH, what is the percent yield? So we need to start by balancing the chemical equation. So I've got carbon monoxide reacting with H2 to produce, remember that's my arrow, CH3OH. So when I go ahead and balance this, I have 2 hydrogens, two H2s, so 4 total hydrogens to match the 4 from the CH3OH on the right. Okay. And I'm good on my carbons and my oxygens. So 1, 2, and 1 are my coefficients. So determining what information is given to you, I have a reactant, right? 8.60 grams of H2. How do I know that's a reactant? Well, it's over here on the left side of my equation. It says it reacts with the CO. Everything is pointing toward that being a reactant. Now the next piece of information I have is the 35.7 grams of CH3OH. Well, it says produced. It's on the right side of my equation, so that's a product, right? My product is 35.7 grams of CH3OH. So determine the actual yield. I need to pick which one of these is my actual yield, the 8.60 grams of H2 or my 35.7 grams of CH3OH. Now, because it's an actual yield, yield has to be a product, which means the only option I have here is the CH3OH. So produced in the experiment was my 35.7 grams of CH3OH. I'm not going to use that number again until I get down to step 5. Step 4 wants me to calculate theoretical yield. Well, I know that means stoichiometry. So when I'm calculating the theoretical yield, that's when I'm starting with that reactant. So I've got my 8.60 grams of H2. Now some of you might be going, well, what am I trying to calculate here? What am I making? That is your actual yield. You're going to want to know your grams of CH3OH. I know how much I did get. I now need to figure out how much I should have gotten using my 8.60 grams of H2. So if this is a grams to grams problem, I know it's going to be 3 steps. Okay, so the first thing I need to do is get grams of H2 out of grams. I need to get that to moles. So grams to moles, I need molar mass. Now, grams H2 is here, so I know grams H2 is on the bottom. So the molar mass of H2 is 2.02 grams, and we know molar mass is always 1 mole. So now in the middle, right, I need to go from moles of H2 to moles of the CH3OH. That's using a molar ratio from my chemical equation. So for H2, I see my coefficient is 2, so 2 moles H2, and my moles of CH3OH is 1. So I've got 1 mole of CH3OH on the top. Last step, I now need to get from moles of CH3OH to grams of CH3OH. So I need the molar mass of the CH3OH. So since moles was on the top here, I got 1 mole on the bottom, and oh lord, I need to calculate that molar mass. So let's see, carbon is 12.01. I've got a total of 4 hydrogens, so add 4 times 1.01, and then oxygen, I add 16. That's going to give me 32.05 grams. Okay, I've set everything up, so I've got 8.6 divided by 2.02 divided by 2 times 32.05. That ends up getting me 68.2 grams of CH3OH, right? That's how much I should have gotten. Now, I know from step 3 I did not get that much. I got 35.7 grams of CH3OH. So I'm going to do my actual over my theoretical. So 35.7 grams divided by 68.2 times 100%, I get 52.3%. Now, sig figs don't really care, right? We're going to go for 1 decimal place is good enough with percentages. Right? So 52.3% is my answer. Okay, here's a simpler example. What is the percent yield of an experiment if the theoretical yield is 16.8 grams, but only 15.0 grams were produced in lab? So determining which one is my actual and which one is my theoretical. The actual yield is what I got in the lab. So 15.0 grams is my actual. Theoretical, it tells me that 16.8 is the theoretical, so 16.8 grams. So my percent yield, I've got actual over theoretical. So 15 divided by 16.8 times 100%. Remember, I only want 1 decimal place for my answer. I got 89.3%. That's nice. There was no stoichiometry involved there. Here's one that is going to have some stoichiometry. So adipic acid, H2C6H8O4, is made in the reaction below. Okay, and it's already balanced for me. That's great. The controlled combustion of 25 grams of cyclohexane. Oh, okay. Well, I've been given a piece of information. So I'm looking and I see cyclohexane C6H12. That's on the left side here. That is a reactant. So I'm going to put that under reactant. It will produce 33.5 grams of the adipic acid. Well, the adipic acid, that big, huge formula here, that's on the right. That is a product. Right? Calculate the percent yield. So the actual yield, again, is that product, 33.5 grams of the adipic acid. To find my theoretical yield, I'm going to start with my reactant, the 25 grams of the cyclohexane. What am I calculating? Grams of adipic acid. So this is a grams to grams problem. It's 3 steps. I'm going to start with the molar mass of the C6H12. So I pull out my calculator. I got 6 times the molar mass of carbon, 12.01. I add 12 times the molar mass of hydrogen, 1.01. It's 84.18 grams. And molar mass is in 1 mole. Now to get from cyclohexane to adipic acid, I need those coefficients. So here's my cyclohexane with its coefficient of 2. And then here's my adipic acid also with a coefficient of 2. Now to get this to grams, I need the molar mass. So moles to moles here, 1 mole on the bottom. And then a very long molar mass problem here. So I've got 10 total hydrogens, so 10 times 1.01. I add 6 carbons, so 6 times 12.01, and 4 oxygens, 4 times 16. That's huge. It's 146.16 grams. So pull out my calculator, 25 divided by 84.18 times 2 divided by 2 times 146.16. It spits out at me 43.4 grams of adipic acid. So I've got my actual, I've got my theoretical. Time to do some percent. So I have 33.5 grams divided by 43.4 grams times 100% gives me 77.2%. Now some of you at this point might be wondering, can my actual yield ever be greater than my theoretical yield? Well, yeah, it can. So you can get a percent yield of over 100%. Miss Yuria, how is it possible to get more than I thought? Well, the short answer is that you messed up, or not so much you messed up, but your scientific method wasn't quite spot on. So the number one way that that happens is, and you're going to see, we're going to do a lab in some later classes, where you are mixing two solutions, and when you mix those two solutions, you get a precipitate. Remember, a precipitate is a solid that forms in solution from a chemical reaction. So now you want that solid out. So you filter it. We've learned about separation techniques and filtering and all that good stuff. So you filter it, you've got your solid, huzzah. The problem is, if you don't dry that solid completely, you're going to have some of your solution or water or whatever it is still in your sample. So that'll make it seem like it weighs more than it actually is. So your actual yield can be higher than your theoretical. That's just one example of how things can go wrong. Other ways is that it could react with things. There's contamination, there's byproducts, there's a million different ways that lab can go wrong. But generally it's under 100%. Doesn't mean it has to be under 100%. Okay, example number 3. The plot thickens. So lithium nitride is prepared by the reaction below. And looking at this reaction, it is balanced for me. What is the percent yield of lithium nitride if 76.8 grams of Li3N? Okay, Li3N. It's on the right side. That's a product for me. If this is recovered from reacting 56 grams of nitrogen gas, okay, nitrogen gas is here, that's a reactant, and 56 grams of lithium metal, oh no, 2 reactants. I've got alarm bells going off in my head right now. If I've got 2 reactants, I know that this is going to be a limiting reactant problem, ugh. Right? We'll get there. I'm going to start by determining my actual yield. Remember, actual yield is a product, so it's the 76.8 grams of lithium nitride. For theoretical yield, I'm going to have to do 2 lines of stoichiometry, right? I'm going to have to do one for the N2 and one for the lithium. So here's my 56 grams of N2. I'm going to get that to grams of lithium nitride. So I've got 3 steps here, starting with molar mass. The grams on the bottom because grams was on the top. Molar mass is always 1 mole. Now I need coefficients. Remember, when there's no coefficient, that is 1 mole of N2. To lithium nitride, I need 2 moles of Li3N. And now I need to get this to grams, right? Because this is in grams. So 1 mole on the bottom, moles and moles. Then I see 3 times lithium, which is 6.94, plus the nitrogen, which is 14.01. I've got 34.83 grams. So beep, boop, boop, beep, some stoichiometry. I get 139 grams of lithium nitride. Okay, I'm not going to do anything with that yet, because I don't know if that's really my theoretical yield yet. I have to deal with the 56 grams of lithium before I can do anything with that 139 grams of lithium nitride. So grams to grams, it's another 3-stepper. So I'm going to take the molar mass of the lithium, 6.94 grams, that's in 1 mole. Now I need lithium, right? Lithium's got a coefficient of 6, so 6 moles of lithium to the 2 moles of lithium nitride. And then this last part is exactly the same because I'm going from moles of lithium nitride to grams. So 1 mole lithium nitride, 34.83 grams. So beep, boo, boo, beep. I get 93.7 grams of lithium nitride. Now, I know based on limiting reactant, I have to go with the least amount because once I produce that amount, I'm out of reactant. So my theoretical yield is the 93.7, not the 139. right? Lithium here is my limiting reactant. N2 is going to be excess. There's going to be some left over. I don't care, right? So I'm going to use 93.7 when I calculate percent yield. So I got 76.8 grams divided by 93.7 grams times 100%. That's 82.0%. This is as hard as these problems get, right? We don't go more complicated than this. So there is practice for you in page 8 in your notes. At least I believe it's page 8. So you are going to pause this video, work on the practice problems. When you're done, I unpause the video and you will see me explain. So pause now. Are we back? Welcome back. All right, hopefully it wasn't too terribly difficult for you guys. So we're going to start with practice number 1. So what is the percent yield of an experiment if the theoretical yield is 25.6 grams, but only 18.9 grams were recovered in the lab? So the actual yield, what I got in the lab, is 18.9 grams. The theoretical yield, it tells me, is 25.6 grams. So 18.9 divided by 25.6 times 100 gives me 73.8%. Number 2. Methanol, CH3OH, can be produced through the reaction below. If 75 grams of carbon monoxide 75 grams of carbon monoxide is a reactant, so that's a reactant given, reacts to produce 68.4 grams of methanol. That is a product, so here we are on the product side. What is the percent yield? So my actual yield is that product. Percent yield, I'm going to start with the carbon monoxide. To go from grams of carbon monoxide to grams of methanol, that's 3 steps. I start with the molar mass of this in 1 mole. Molar ratio, I've got a coefficient of 1, and then the molar mass of methanol, right, moles on the bottom, and then 32.05 on the top. It gives me 85.8 grams of methanol. So 68.4 divided by 85.8 times 100, that's 79.7%. All right, last one, the reaction of ethane, C2H6, with chlorine gas will produce hydrochloric acid and chloroethane, C2H5Cl. Calculate the percent yield if 300 grams of ethane, okay, ethane is over here, that's the C2H6, that's a reactant, reacts with 650 grams of chlorine, chlorine is there, that's a reactant, to produce 490 grams of chloroethane. All right, so 490 grams, that's a product, right? Chloroethane is over here. So my actual yield is that product. Theoretical yield, I'm going to have to do 2 lines of stoichiometry. This is a limiting reactant problem, right? 2 reactants. So starting with my 300 grams of ethane, right? 3 steps, starting with molar mass, right? Grams to grams here, top and bottom. Now I need coefficients, 1 ethane to 1 chloroethane. And then the molar mass of the chloroethane, moles on the bottom. I got 64.52 grams. Beep, boop, boop, beep. I got 643 grams of chloroethane. I'm going to leave it there. I need to do the other line before I decide what my theoretical yield is. So 650 grams of chlorine. Grams to grams is 3 steps, starting with this molar mass, 70.90 grams, 1 mole of chlorine. Coefficient in front of chlorine is 1. Coefficient in front of chloroethane is 1. And then this is the same, right? No different here. When I calculate that, I get 592 grams of chloroethane. That is my theoretical yield, the one that is less. All of this useless to me. So percent yield is 490 over 592 times 100%. That is 82.8. All right, thank you guys for watching the percent yield, and I will see you in our next video.